Okay, this is our last video concerning identities when the del operator is operating either on a position vector or one of the scalar functions. This, of course, is what the position vector is, and the magnitude of the position vector, r, is just a scalar quantity, and it's a function of x, y, and z, which is just the square root of x squared plus y squared plus z squared. What we want to show in this video is that the Laplacian of any function of r is equal to this identity. So let's set this up. We know that from its definition, this means taking the divergence of the gradient of that scalar function. And if you've watched the previous videos, you will know that that's equal to the derivative of the function times the gradient of r, where r, of course, is the magnitude of the position vector. And if you've watched the earlier videos, you will know that the gradient of the magnitude of any position vector is equal to the unit position vector. Or we write it like this. So this is equal to 1 over r times this derivative multiplied by the position vector r. So that's what this is. So we rewrite our problem again like this. This dot del f of r, that's equal to del dot this quantity, 1 over r f prime of r times the position vector r. So here we have the position vector is being multiplied by the scalar quantity, and in previous videos we learned how to handle this situation. This is equal to the gradient of this scalar you take the dot product of that with the vector, in this case that is the position vector r, plus it is the scalar quantity 1 over r times the first derivative of the function, and that's being multiplied by the divergence of the vector. In this case, it is the divergence of the position vector, and that, if you watch the previous videos, you know that equals 3. So we have then that del squared f of r, that's this, that is equal to 3 divided by r times the first derivative of r plus the gradient of this scalar, 1 over r times the first derivative. You take the dot product of that with the position vector r. And again now, if you've watched the previous videos, you know that that's equal to the derivative of this with respect to r times the gradient of r. And taking now the derivative of this product, we'll have this times the derivative of 1 over r, so that will equal minus this f prime of r divided by r squared. That's this times the derivative of this. Then we're also going to have plus 1 over r times the second derivative. So we'll have f so that's this quantity here times delta r. We know what that is. That's the unit vector. So times the position vector. That is the unit position vector. We discussed that up here. We've shown this many times in the previous videos. So here then we have this. So we can say this is going to be equal to minus the first derivative of the function divided by r cubed plus the second derivative of the function divided by r squared, and that is being multiplied by the position vector r. So let's see where we are at. We have this expression here equals this. And what are we supposed to do with this expression? Which is this. We're supposed to take the dot product of it with the position vector r. So we're supposed to take the dot product of this with the position vector r. So that's write it out explicitly so you don't get mixed up. We have this right here, del of 1 over r f prime of r dot r, that's equal to this minus f prime of r divided by r cubed plus the second derivative divided by r squared times r dot r. This is that right there. So this is just going to be r squared. R dot r is r squared. And this will be equal to then minus the first derivative of our function, r squared divided by r cubed divided by r, plus the second derivative. Okay, so if we go back now up to here, we've determined what this is. That's this, and we also have this term. So we have now del squared of f of r equals this term, 3 over r times f prime of r, minus this term, f prime of r divided by r, plus this term. And this is going to equal d minus 1 is 2, so we have 2 over r times the first derivative plus the second derivative. And that's what we were supposed to show. That's the identity. So there it is. And you will see this quite often if you take courses in advanced mechanics and electromagnetic theory. You'll see this a lot in different mathematical physics textbooks and engineering textbooks. This identity right here. Okay, that takes care of for this video. Come back, join us for some more videos, and we'll solve some more problems.